So this video is going to be a little bit different than the ones we have done in the past, in that this is a continuation of something we were working on in class, and I don't think we're going to get to finish it. So we were talking in class on Wednesday, the 15th, about using a stack to do quicksort. So we had implemented as part of your, I guess, pop quiz or during a 1-2-4 exercise, how to take a stack and reverse all of the elements in it. So I had you all write this get reverse method that takes a stack and returns a stack of the same size, but with all of the elements in the reverse order. And that's actually going to come into play when we write our do QuickSortStack method. So as a reminder, what do QuickSortStack does is it takes this method, takes in a stack of unsorted sorted integers and returns a sorted, returns a stack of the same integers in sorted order using the quicksort algorithm. So notice that that we're using quicksort here, and we learned quicksort on arrays, right? We learned it on arrays, but here we're doing it using stacks as the underlying data structure, right? So obviously we're not going to return null. This is just a placeholder so that it sorts. So we need a couple base cases here, right? Because quicksort is recursive, right? So what are the base cases that we should have for quicksort? Well, one base case is, I guess we could put them together. But the base case for quicksort is only one element. Stack. Or no elements, right? So the stack could have nothing in it. So we have a couple methods to do that. So if it has no elements, what's the method that we use on a stack? Well, to find out if the stack is empty, we use, so if in stack dot is empty, or in stack dot get length is less than or equal to 1, right? In that case, what do? We return in stack. We don't need to make a new stack. We can use the same one because it only has one item, or it has 0 items. And that's it. Okay, so now that that's out of the way, we know we have some stack with at least 2 items. And what does quicksort tell us to do? Well, it says to pick a pivot. So pick a pivot value. Well, in this case, we're going to take, we really don't have that many options, right? We can take the top item of the stack or not take the top item of the stack, right? So in this case, we're going to make integer pivot equal to in stack dot pop, right? We're going to take that top element off of the stack and we're going to make it our pivot. So once we have our pivot, what does quicksort tell us to do? Well, it says to split the problem in 2. So since we don't have an array to be able to send ranges, and here we're only passing a stack back and forth, what does that mean we need to do? It means we need to make 2 new stacks. One for those things that are less than the pivot and one that's for the things that are larger. So let's make one that's less equals new stack, and one that's more, new stack, right? 2 new stacks for the things that are larger and smaller than the pivot value. Okay. And so now we need to fill them. How do we fill them? Well, if the front thing on the stack is bigger than the pivot, we're going to put it in more. So let's write that as an if statement. If in stack dot peak, right? Because that'll tell us about the front element without taking it out. If peak is greater than pivot, then what do? It goes in more, right? More, we're going to push onto it in stack dot pop. So we're going to take that element, we're going to take it from our in stack, and actually I'm going to make this a little bit nicer so we can read it. But it says if that top element is larger than the pivot, we're going to push it onto the more stack, right? And we're going to take it off the in stack. If in stack dot peak is less than the pivot, let's say less than or equal to the pivot in case there's repeats, right? Then we're going to do the same thing with less. So less dot push in stack dot pop. So, okay, so that takes the top thing and either puts it on more or less. Do we just do that once? No, we have to keep doing that while stuff is in the stack. So how do we know if something is still in the stack? Well, we know in stack dot is empty is going to be false, right? So it's just like we did up here when we checked this. So while the stack isn't empty, we're going to take stuff off the front of it and either put it on more or less. We're going to indent that to make it nice. So we're going to add a comment for each element in the stack. Put it in one of the 2 new stacks based on its value with respect to pivot. Okay, so now we have this stuff in 2 stacks, and what does quicksort tell us to do next, right? So here, this is sort of the partition stage of quicksort, and now we need the recursive call. Right? So what is that going to look like? Well, we need to do quick sort stack, and we need to do it first on more. But we know that do QuickSortStack returns a stack, right? It doesn't alter the stack that we gave it. So we need to put it somewhere, and we need to put it back in more, right? We saw an example of this in one of our labs before, in the amino acid lab where we were doing sort, right? And we need to do the same thing with less equals do quick sort stack less. So now we have 2 sorted arrays, or sorted stacks, sorry. And what do we need to do now? Well, we need to create the stack that we're going to return, right? So in this case, our quicksort has a merge step. Because now we have two sorted arrays. Instead of doing it in place, we sent it off to be done by somebody else. Right? So we need to make our out stack, just like sort of like we did up here with reverse. Right? And we know in these, we're guaranteed that so I forgot to say it up here, but the minimum value is at the top of the stack. So the minimum of all the things that are less than the pivot is at the top of less. So we basically need to empty less into our out stack. So while not less dot is empty, we're going to say out stack dot push less dot pop, right? And it's going to do that over and over again. And then we push in our pivot, push pivot, right? Because notice that we had already popped it out. So it didn't get put into either less or more. And then we need to take everything out of more. But now out stack contains all of the elements in reverse sorted order. So what do we do? Right? So everything is now pushed into this out stack, but it's in reverse because we took the minimum thing and put it at the bottom. Well, that's why we wrote this get reverse, because now we need to return get reverse of out stack. Right? Because we put everything in minimum first, but we want the output to be minimum first. Okay? So do we think this works? Should we try it? No pointer exception. Do QuickSortStack line 49. Here. Oh, I see what I did. So why did this get a null pointer exception? Because peak, when you do peak, it gives you that top value. The top value can either be greater than or less than. Why should that give a null pointer exception? Well, it's because inside this if statement we ran a pop, which changes this value. Right? So you might have popped out the last thing. So here we need an else if. Right? And you can see we gave it 1, 7, 12, -5, -12, 70, and 0, because I have this printed up here. And it returns -12, -5, 0, 1, 7, 12, 70. Right? It does exactly what we asked it to do. Right? And it did that through these stacks. So when we presented the sorting algorithms, right, we presented them using arrays, but really it's the algorithm itself, not necessarily the data structure. So we showed that you could use linked lists for them. Now we're showing that you can use stacks. And what we might talk about next week is how we can use queues, right? underlying stacks and queues are linked lists or arrays, right? But it provides sort of an abstraction for us. So this is how you write quicksort for stacks, right? One example of it. You could do something a little bit different probably, but this is using the idea of quicksort and implementing it using a stack data structure.